Okay, so in this video, we're going to take a look at the equivalent of slope fields when we looked at how we could picture the dynamics of one single differential equation. Now we're going to look at how we can visualize the dynamics of systems of differential equations by sketching a vector field, and now we're working in the phase plane in the xy plane. So we're looking at the relation between the two dependent variables x and y. So this is what's called the vector field. And just like with our slope fields, these are like signposts that are telling us if you start at such and such a point, here's the direction that the solution through that point is going to move. So I'm going to take a look at a table. We're going to create a little table to map out some of these values. So let's start with the point at minus 2, 3. So the point at minus 2, 3, that would put us, for example, right over at this point over here. And we can see from the picture, I drew in some. I caution you that these are not necessarily drawn to scale, but I've drawn some vectors in, and we can see that this one heads down and to the right. And we can check why that is so. So if I were to plug this initial condition into the differential equation, then x prime would be y minus x, and that would give me a positive 5. And if I plug this into the differential equation, dy dt, I would get minus y, which gives me minus 3. And that's why we're moving to the right and down, because x prime is positive and y prime is negative. But that vector that I drew over there should have slope, which is equal to y prime. So the way that we find dy dx is we take the slope of dy dt and divide by dx dt. So for us, we would take minus 3 divided by 5, and that would give us minus 0.6. And so that's what's drawn right over here with this vector. It's pointing down and to the right. And then we can continue on and do this at every other point. And I should say that the size, the length of these vectors doesn't tell us any information. They are all the same length, but it's really the steepness, the direction, which is what we care about. So at 0, 1, we're over here on the y-axis. And here, when I plug in 0, 1 into the equation for dx dt, then I would get 1 minus 0, so I get 1. When I plug into the differential equation for dy dt, I get minus 1, and dy dx would be the minus 1 over 1, which is negative 1, and that is this vector over here that we've drawn over here. And so then we can take a look at some special vectors in particular. So I'm going to take a look at any vector that's sitting on the x-axis where y is 0. So that would be a vector like this, and like this, and so on. So for any of these vectors, we can see in the vector field, these are all horizontal vectors. And that's because when I plug something that has a y-coordinate of 0 and x, some arbitrary x-coordinate into the differential equation, then we get that dx dt would be minus x, and dy dt is actually 0. So when I take dy dt dx over dx dt, I get 0. And so that's why all of these vectors are horizontal. And one thing that we should pay attention to is a horizontal vector can point to the left or to the right. And so it's going to be the sign of dx dt, which is going to determine whether we go to the right or to the left. And so for all of these points over here, when x is negative, we can see that x prime would be positive, right? Because x prime is minus x. So if x is negative, minus x is positive. So x prime is positive, and therefore these are pointing in the positive direction to the right. And similar analysis is going to give us the reason why these vectors over here on the other side are pointing to the left. And we have a similar interesting behavior going on with points on the line y equals x. So all of these points here and here and here, where the x coordinate and the y coordinate are equal to each other. And we see that these are pointing vertically up, or possibly they're pointing down if we're over here. And the reason why is when I plug this, points that have x and y coordinates equal to each other, into the differential equation for dx dt, we would get 0. However, dy dt is going to depend on the sign of y. So that would give me minus y. And so when I take a look at dy dx, I'm getting something like minus y over 0. So when we divide by 0, that means we're getting things that are either pointing directly up, positive, and have slope positive infinity, or pointing directly down. And for the same sort of analysis, if we want to determine whether they point up or down, and we should, we would, for example, say, well, if y is negative, then y prime, which is equal to minus y, would be positive. And so that's why all of these vectors over here are pointing up, and for similar analysis, we would see that all of these vectors are pointing down. And typically, we use technology to get a robust-looking vector field, but sometimes it's useful to get your hands on these and actually plot a couple by hand to get a sense of what information these vector fields are conveying. And just like with slope fields, when we're looking at these vectors, they give us an indication of how our solutions are behaving. So for example, if I were to start over here, I can see this solution would go straight in to the origin, and over here we would come down and to the right, and it looks like we're heading back towards the origin. So these particular vectors that point straight up or possibly straight to the left or to the right, these are going to be of particular interest to us in determining the dynamics, and that's what we'll take a look at next.